In this video, I'll talk about the acetoacetic ester synthesis. This is one of the great ways of making a new carbon-carbon bond and eventually eliminating most of the starting material, but still have those new carbon-carbon bonds kind of stayed intact. And at the end of the day, you will get a ketone or possibly sometimes an aldehyde as well, depending on how you starting it out, with a longer chain. So this is the starting material that's called acetoacetic ester. So we have an ester function group. We also have a ketone function group. We have this alpha position that's being shared by both of these carbonyls. As a result, the proton that you have in there, technically two of them, they are going to be fairly acidic, starting out with their pKs around 10 and 11. And I'm going to be doing a bunch of these steps in here, and we're going to be seeing how these steps kind of adds on to this particular molecule. So let me go ahead and change the colors on them, and I'm going to go ahead and use this, let's say. So the first step, if you think of it, is actually going to be an acid-base step. So we have an O CH2, CH3 minus, that's and a strong enough base. And another thing you want to make sure you're using the base that's alkoxide base, and on the top of that, it's the same sort of alkoxide that you have on the ester, so that even if there is a little bit of a esterification, you still ended up getting the same type of stuff. If you're using a hydroxide, you also have a fear of hydrolyzing the ester, so you don't want to be using an hydroxide base, rather than the same alkoxide base that you got on the ester side here. So the first step is the removal of this proton here. And you don't necessarily have to kind of draw the mechanism, but you think through the steps. That's what's going to happen in the first step. I remove this proton, and it created an enolate that's going to be fairly stable because of the resonance that it can make both of the ways. So remember, I didn't lose both of the hydrogens. I lost only one hydrogen, so I can draw the other one if you want. And this will be stabilized by the resonances on both sides. So I'm not going to draw that. And the next step is the CH3Br. So what does CH3Br would do? Well, that would now run a SN2 type of mechanism where I can say this is going to come down and attack here, and then this would come out here. And at the end of the day now, I'll have a new bond. So the hydrogen is still there, so I'll leave that there for a minute. Now I got a methyl group attached to this because this CH3Br, if I want to change that color, was this guy right here. And I'll leave this one with this color. Okay, so I have now a metal grip installed in there, and there's a good chance that you probably just stop the reaction here and maybe do the fifth step, but you could actually remove the second set of proton as well because it's still fairly acidic enough. So when I'm using the second step of uh, second base here, so that would be number three in this case, and I'm using NaO. CH2, CH3. So that would do the same thing. I will have this removing this proton here, and this is going to go ahead and create a negative charge on here. I get on a negative charge. It already had a methyl installed. Now I get a negative charge, another enolate created, and then in the next step, I'll have an ethyl bromide. So that would do an SN2 here, where this negative charge would attack this carbon here, and this would leave, and now you have another set of alkyl group installed there. So I had previously a methyl there. Now I'm going to have an ethyl group attached there. So I don't really have any more hydrogens on that alpha position, so I can go ahead and stop it right there and run the hydrolysis. So the hydrolysis is typically done under acidic condition and along with the heating. So it's going to do two things while you're doing the hydrolysis. I'm going to make a little bit of space here. Move this down a little bit. So when you're running the hydrolysis here, the first step on the hydrolysis would be conversion of this to an acid. Because remember, the hydrolysis of esters will take it back to the acid. So hydrolysis of ester will take it back to the acid. And your side product here would be CH3, CH2OH. That would be coming from this guy right there. Okay, and now this is something interesting happen in a sense that anytime you have two carbonyl groups, especially when you're run the hydrolysis and made the acid here, and you're heating it up, so you're not going to be seeing two separate steps, but just seeing in one step in there along with heating. So what happened is there you have two carbonyls that are kind of close enough, kind of in a only separated by one carbon, and one of that carbon has to be in an acid. Like you can have both of them to be an acid, but at least one of them has to be an acid to do something called in a decarboxylation, so it can lose in a carbon dioxide. And the way this really works, if I just kind of rearrange this in terms of drawing, um, let me go ahead and draw and a carbonyl here. I'm going to go ahead and draw the acid on this side. So what happens is like here, one, two, three, four, five, and six kind of makes in a six-member ring where this hydrogen is kind of close enough to the other carbonyls. So that's what helps to do around the decarboxylation here. So I can say that I will have this kind of going in there to grab that proton, and then this would be coming down here to make the carbon dioxide, and this bond will be coming down here to make this double bond here. So at the end of the day, this part of the molecule right there makes the carbon dioxide. So that's why it's called a decarboxylation here. So in this step, I'll first make CO2 that will go away. And then that one is obviously coming from here. So we have already drawn that. And then the rest of the molecule would look something like this. I'll have an enol type of molecule kind of formed in the beginning. And then I still have an ethyl group there, just trying to keep the colors in there. And then I got a double bond there. So that makes the enol, but that enol would get tautomerized to an keto form. So your end product is still going to be the keto product. I'm running out of space there. Now I would have a double bond right there. So I still have the left side of the Ceto kind of intact in there. If I go back to the starting material and be like, okay, what changing I'm really making, or what changes I'm really making here, I can say that, okay, I got this guy right there is still there, all right? And I can say, let's use another color here. This right there, which was the esters hydrolysis, is kind of an ethanol here that we kind of lost. And then we had a CO2 kind of gone away. So CO2 was this one right there that we kind of made right here. And then you had, let's say, use a different color here. You have the CH3Br, that one is right here. And then you also have this right there, ethyl group. Which one is this right there? So this is really one of the great ways of creating a carbon-carbon bond and still ended up getting it in a ketone at the end of the day, but with in a longer chain. So sometimes you have to do that. And this is in a very, even though it kind of looks a little bit of intimidating in the beginning, but it's kind of in a very straightforward reaction as long as you understand the steps, what's really happening in every single step in terms of making the enolate and then using that enolate in the form of an nucleophile and doing it in SM2 reactions and moving along. Now remember, you could very well just do this first two steps and run in a hydrolysis and decarboxylation. So you don't necessarily have to remove both of those protons. You can just remove only one of them and then run the hydrolysis and the decarboxylation as well in that meantime. So that's something you want to keep in mind that you could see something like that as well.